Hi everybody! In today's video, we are going to be going through the notes for lesson 9.3, which is all about something called volumes by revolution, and today we're focusing on what's called the disk method. Let's start with a quick recap of what we know so far. So far, we know that we can find the area of a region that is between two curves using an integral. We also have learned that we can find the volume of a three-dimensional figure using an integral by adding each of the areas of the slices. That's what we did in lesson 9.2. Today, we're going to focus on finding the volume of a solid of revolution using definite integrals. So we're going to be focusing on revolving shapes today. Just like with our previous lesson, it's always easiest to understand what's going on here if we have a good visual. So I'm going to go ahead and show you a visual of what's happening before we start the notes today. Today we're going to be working on doing something called revolving a figure. Let's see if this website will load for me. When we revolve a figure, what we're doing is we're spinning that shape around a line. So we're revolving it, we're spinning it. So what we're going to be doing today is we're going to be taking a graph, like for example, the one shown here, and we're going to be revolving it. And I'm going to go ahead and use this slider to show you what it looks like when we revolve this shape. If you look at this shape, do you see how it's revolving around the x-axis? As we revolve that flat shape, and we imagine it sort of fills itself in as we go, what we're being asked to do is find the volume of that solid figure, that three-dimensional shape. Now, I want you to look at the very end of that shape. If you imagine looking at one slice, each of the slices of this three-dimensional figure would be shaped like a circle because we're creating this figure by spinning a graph around in a circle, around a line. Because of that, we call this the disk method because each of those little slices, if you imagine slicing it, would be like a very thin disk. Let's go back to the notes and let's write some of that down. So the disk method is the idea that if a region of area is revolved around a line, and it could be a line that's horizontal or a line that's vertical, the resulting solid is called a solid of revolution. And the reason we call it that is because it's formed by revolving something. The line that you're spinning your shape around is called the axis of revolution. So it kind of tells you this is the line about which everything is being spun. An example would be, suppose the region R shown is revolved around the y-axis. So let's kind of use our imagination. If we take this triangle and we spin it around the y-axis, the other side of this three-dimensional shape would end up over here looking like this. And it would be spinning and it would create circles. If you imagine that that's a solid three-dimensional figure, that figure is going to be a cone. And we can find the volume of that figure just like we used integrals to find areas and to find volumes where we sliced things. We can find the volume of this figure by using an integral. When we revolve a figure, each cross section is going to be shaped like a circle. Therefore, we can use the same method we used when we did volumes by cross sections to find the volume of these figures as well. But this time, instead of having cross sections that are shaped like squares or rectangles or triangles, all of our cross sections are going to be shaped like circles. And the area of a circle is always pi r squared. Now, I do want to make sure to point out that the radius of a circle goes from the center of the circle to the outer edge. So in this picture, the radius of the circle would be this distance that I just drew. It's not going to be all the way across. It's not going to be 8. That really big radius all the way at the bottom of this cone is going to be 4 halfway across. We call this method the disk method because each circle is shaped like a flat disk. And we're just adding up all those flat disks to build a volume. Let's go ahead and look at some examples. The first thing we're going to talk about is when we revolve our shapes around the x-axis. So we're going to do an example where the x-axis is the axis of revolution. When we revolve a region around the x-axis or any other horizontal line on the graph, any horizontal line, we always set up our integral with respect to x. So if we are going around the x-axis, we do everything in terms of x, or any other horizontal line, we do everything in terms of x. For example, suppose that the region contained by the graphs of the function f of x is equal to the square root of 4 minus x, the x-axis and the y-axis is revolved around the x-axis. The first thing to notice here is that it says in the directions we are revolving our shape around the x-axis. So we're going to be rotating, and that means all of our cross sections are going to be circles. So right away, I'm going to write down that my area formula here is going to be pi r squared. Now I'm going to sketch a graph so that I can visualize what's happening. I'm going to graph 4 minus x, the x-axis and the y-axis. So here's my y-axis. Here's my x-axis. The graph of the function 4 minus x is going to be a square root graph that was shifted to the right 4 spaces and flipped horizontally. So it's going to look like this. Now you'll notice it says in the instructions, we want the area that was contained by that graph, the x-axis and the y-axis to be revolved. So it's going to be this area of the graph right here that we are rotating. And we are going to rotate that area around the x-axis. So sort of the bottom of that shape when we spin it is going to look like this. And each of my slices is going to be a circle. Now in this picture, the radius of that circle is going to be the distance from the function to the x-axis. Not all the way to the bottom, but just to the x-axis. Going back to my area formula, in this area formula, r is going to be equal to the top minus the bottom here, the distance between those things, which is the square root of 4 minus x. Now, if I plug that in, my area formula is pi times the square root of 4 minus x squared. And since a square root and a squared are inverse operations, that cancels, and I just get pi times parentheses 4 minus x. That means that my volume here is going to be the integral from my beginning x value, which is 0, to my ending x value, which is 4. And I'm going to have pi times 4 minus x inside of my integral. Now we're going to be doing a lot of examples on this in this notes, but for this one, this is the only time I'm actually going to go through doing the antiderivative and evaluating this, simply because I don't want to make this video too long. The process is going to be the same as the way we've done antiderivatives and evaluated integrals for a long time now. The first thing I'm going to do is I'm going to take this pi and I'm going to factor it out of the integral. The reason is because I know that I'm not going to be able to, multiply by pi. I don't know how to do that in my head, and I don't have a calculator here. So what I'm going to essentially do is just sort of save the pi for the end, put the pi on the outside. I'm going to evaluate the rest of the integral. Now, the antiderivative of 4 minus x would be 4x minus 1/2 x squared plus c, evaluated from 0 to 4. If I substitute in my numbers, I have pi parentheses. If I plug in the number 4, I get 16 minus 4 squared is 16, and half of that is 8, plus c, minus if I plug in 0, I just get c. And so since 16 minus 8 is 8, my volume here of this solid would just be 8 pi. Again, that's the only problem where I'm actually going to work out the antiderivative and the integral by hand. You should be able to do most of these problems without a calculator, but I'm just not going to work all of that out in the notes today to avoid making the video super long. For problem number 2, we're going to look at an example where we revolve our shape around the y-axis. So when we revolve around the y-axis or any other vertical line, just like the y-axis is vertical, we always set everything up with respect to y. So if you see revolve around the y-axis or vertical lines, you're going to set everything up with respect to y. An example would be, suppose the region contained by the graphs of f of x equals x cubed, y equals 8, and the y-axis is revolved around the y-axis. Now, there are a couple things I know right away. The first thing I know right away is that all of my slices are going to be circles because I'm revolving something. So my area formula is going to be pi r squared. The second thing is I know I'm going to set everything up with respect to y because I know that I'm spinning my graph around the y-axis. So I'm rotating it around this line right here. Now, x cubed looks like this. And the line y equals 8 looks like this. Since I'm taking the region of the graph that's contained by those two graphs and the y-axis and I'm revolving it, it would be this region of the graph right here. And I'm revolving it around the y-axis. So the other side of this region would be right here, and each of my slices would be circles. Now, the radius of one of these circles would be the distance between the y-axis and this graph. Since I know I'm going to do everything in terms of y here, I'm going to convert this equation to be in terms of y, which means I'm just going to cube root both sides, and I get that x is the cube root of y. So my radius here is going to be that the radius is equal to the cube root of y minus 0, which is just the cube root of y. Therefore, my area formula, when I substitute that, is going to be pi times the cube root of y squared. Now, my volume is going to be the integral from my lowest y value, which is 0, to my highest y value, which is 8, of pi times the cube root of y squared dy. And then I would do the antiderivative, I would plug in my numbers, and I would simplify my answer. When I do all of that work, I should get 96 over 5 pi. And you can feel free, of course, to type that into your calculator and make sure that that's what you get. Next, let's take a look at number 1 for our examples here. So in each of these examples, we're going to have to read the directions carefully, decide if we're integrating with respect to x or with respect to y, and then make sure that we sketch a picture and set up our volume formula appropriately. So for example 1, it says find the volume of the solid of revolution. So right away, I'm seeing solid of revolution. I know my slices are all going to be circles. Generated when this graph and when the area bounded by this graph and the x-axis from -1 to 1 is revolved around the x-axis. As soon as I see that it's revolved around the x-axis, that tells me I'm going to be setting everything up with respect to x. I'm going to go ahead and sketch a picture. So in this problem, I'm revolving a parabola that's been flipped vertically and shifted up 4 spaces, which means it looks like this. And I'm going from -1 to 1. Now, I happen to know that this parabola is going to touch the x-axis at 2 and -2. And so the area that's between -1 and 1 would just be this area right here. So I'm revolving this area around the x-axis. That means that the bottom sort of side of, or part of my volume here is going to look like this. And each of my slices is going to be a circle. Now, the radius of this region is going to be from the top to the x-axis, from the top to the bottom. So I'm going to use the area formula pi r squared. R in this problem is going to be negative x squared plus 4 minus 0, which is just negative x squared plus 4. So my volume, I should write out the area formula first, huh? Pi times negative x squared plus 4 squared. My volume is going to be the integral from my lowest x value, which is negative 1, to my highest, which is positive 1. And then I'm going to have pi times negative x squared plus 4 squared dx. Now, I'm not going to work out this whole problem by hand, but I am going to give you a hint. If you were going to do this whole thing by hand, you would need to multiply out this parentheses before you could do the antiderivative. So you would need to actually write that twice and then distribute. So you would get x to the fourth minus 8x squared plus 16. And then by doing that, you would be able to actually continue and do the antiderivative and plug in your numbers. And when you do all of that, you should get 406 over 15 pi. And that would be your volume. Next, let's take a look at the next example. So it says, find the volume of the solid of revolution. So as soon as I see that term, volume of the solid of revolution, I know that I'm spinning something. All of my slices are going to be circles. When the area between negative y squared plus 1 and the y-axis from 0 to 1 is rotated around the y-axis. As soon as I see that I'm rotating around the y-axis, I know that I'm going to be doing everything with respect to y. So if I sketch a picture of this graph, negative y squared plus 1 is going to look like this. It's going to go to 1 and 1, and it's going to look like this. Now we want the region between the y-axis and then from 0 to 1 on the y-axis, which means we're looking at this region of the graph right here. And y is going from 0 to 1. If we revolve that around the y-axis, the other side of this region would be here, and each of my slices would be circles. Now my area formula, whenever my slices are circles, is pi r squared. And in this case, the radius of each of those circles would be the distance between the graph of negative y squared plus 1 and the y-axis, which has an equation of 0. So it would just be negative y squared plus 1. Therefore, my area formula is pi times negative y squared plus 1 squared. My volume would be the integral from 0 to 1 of pi times negative y squared plus 1 squared dy. Now, again, you would have to actually write that big parentheses that's squared twice and multiply it all out before you could do the antiderivative or anything. But after you do all that and you work out the arithmetic, you should get 8 over 15 pi here as your answer. Last but not least, this is a calculator question, so it would be one that you would have a calculator for on the AP test. Let R be the region enclosed by this graph and the x-axis. Find the volume of the solid generated when R is rotated around the x-axis. So as soon as I'm rotating, I know that my formula is going to be the area of a circle. And because I'm rotating around the x-axis, I know I'm going to set everything up with respect to x. So the first thing I'm going to do here is graph this. And when I graph this on my calculator, I get a picture that looks something like this over the interval from 0 to 2. Now, if I revolve this region around the x-axis, it's going to look something like this. And I'm going to get sort of this vase shape. You're going to get like the shape of a three-dimensional vase. There we go. That looks a little bit better. In order to get the volume of that three-dimensional shape, I'm going to use circles because I'm rotating. And the radius of one of those circles would be the distance between the graph and the x-axis. So my area formula is going to be pi r squared. R is going to be top minus bottom. So in this case, that would be f of x minus 0, which means my area formula is pi times f of x squared. My volume is going to be the integral from my beginning x value, which is 0, to my ending, which is 2. And I know that because it gave me the bounds of the region in the directions. And in here, I'm going to have pi times f of x squared dx. When I actually type that in on my calculator, it's going to give me the answer 50.329 as my volume. All right, that is it for today's notes. Thank you so much. Make sure you do your practice problems, and I'll see you soon.